video, we're going to be discussing the integral test. And the integral test is as follows. So if f of x is continuous, positive, and decreasing on the interval from 1 to infinity, then the sum from n equals 1 to infinity of a sub n is convergent if and only if the integral from 1 to infinity of f of x dx is convergent. Meaning, so since this is an if and only if statement, if the improper integral of f of x dx is convergent, then the infinite sum is also convergent. And if the integral is divergent, then the infinite sum or the infinite series is also divergent. Okay, make sure as you work on through the problems in this chapter and you learn various tests for convergence or divergence that you memorize what conditions are necessary in order to apply them and what you need to check. And in the case with the integral test, there's 3 conditions. You have to check that your function is continuous, that it's positive, and that it's decreasing on the interval that matches the sum of the infinite series. And then you're allowed to apply the integral test. Make sure you always show that you're checking those conditions before you go ahead and apply it. So let's work through some examples so we can see how powerful this test is. So first example, the sum from n equals 1 to infinity of 1 over n is the harmonic series. Now in the previous lesson, we discussed the fact that this is a divergent series. And so now we're going to show this using the integral test. So what I need to do first is define a function. I'm going to let f of x equal 1 over x on the interval from 1 to infinity. So define your interval to match your limits for your index of summation. Okay, so now I'm going to check the 3 conditions. Is f of x continuous on the interval from 1 to infinity? Well, what's the domain of f of x? The domain is all x's such that x doesn't equal 0, but that's fine because on 1 to infinity, 0 is not included, so we're okay. Is f of x positive on that interval? Well, from 1 to infinity, I'm only substituting in positive values for x, so yes, that's going to be satisfied. And then is f of x decreasing on that interval? Well, let's check. Let's evaluate f prime of x. Well, f of x is x to the negative first power, so f prime is going to be negative 1 over x squared. X squared is always positive, so negative 1 over x squared is going to be negative. So it's decreasing since the derivative is negative. Since all 3 conditions are satisfied, then this means it's okay to use the integral test. All right, so for a complete solution, you need to show testing all 3 of these conditions and a complete justification. Now let's set up our integral. So we have the integral from 1 to infinity of 1 over x dx. Now this is an improper integral, so the very first thing I need to do is rewrite this as the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. All right, antiderivative of 1 over x, that's one we're very familiar with. It's natural log of absolute value of x. So we have the limit as t approaches infinity of the natural log of the absolute value of x, and I'm going to evaluate this from 1 to t. All right, so we have the limit as t approaches infinity of natural log. I'm going to substitute in t for x, so natural log of t minus natural log of 1. Let's keep the absolute value there. All right, so as t approaches positive infinity, then natural log of t, think of the graph of natural log, it's going to approach positive infinity. And natural log of 1, that just equals 0. So this limit as t approaches infinity is equal to positive infinity. And if you'll recall from studying improper integrals previously, we said that this improper integral diverges. Well, what does that mean for us? This means that the series or the sum n equals 1 to infinity of 1 over n also diverges, and you must state what test you just used, so by the integral test. All right, and as we mentioned before when we were looking at the harmonic series, even though the terms are decreasing, 1 over n, that's 1, 1/2, 1/3, those terms are decreasing, they're not decreasing fast enough so that their sum converges. And that's the issue with the harmonic series. Okay, now let's investigate another series very similar. So we're going to compare f of x equals 1 over x and g of x equals 1 over x squared on the interval from 1 to infinity, and then we're going to see whether the infinite sum converges or diverges for g of x. So to begin our investigation or comparison, let's graph both of these just on 1 to infinity. So I'm only going to draw values in the first quadrant. Okay, here's x, here's y, and maybe we'll just plot the first 4 x values in these functions. So I'm not plotting a series, or I'm plotting functions. Okay, so f of x is 1 over x. So 1 over 1 is 1. 2 is going to be 1/2. 3 is 1/3, maybe here. And 4 is 1/4. Okay, so this is f of x. Now g of x is 1 over x squared. So they'll have the same initial value here, but at 2, g of x is going to equal 1/4. At 3, g of x is going to equal 1/9. At 4, 1/16. So we can see g of x is decreasing a lot faster than f of x. So do you have any suspicions or guesses as to what's going to happen with this infinite sum? G of x equals 1 over x squared on the interval from 1 to infinity. Now, is it continuous? We have to check our 3 conditions. Well, yes, it has the same domain, all x's, such that x doesn't equal 0. So it's going to be continuous on 1 to infinity. Is it positive? Well, yes. 1 over x squared is always going to be positive, especially on the interval from 1 to infinity. And lastly, I need to check, is it decreasing? Well, let's compute the derivative again. So g prime of x is going to equal, so 1 over x squared, that's x to the -2nd. So this is going to be -2 over x cubed. Remember, you're only substituting in values from 1 to infinity for x. So that's always going to be positive. And so -2 over a positive number, this is going to be negative for all x's that are elements of the interval from 1 to infinity. So yes, it's decreasing. So all 3 conditions checked out, this tells me it's okay to use the integral test. All right, so let's go ahead and do it. Let's set up our integral. So we have the integral from 1 to infinity of 1 over x squared dx. Right away, very first thing, rewrite this as the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx, which equals the limit as t approaches infinity of -1 over x, right? X to the -2nd, antiderivative is going to be negative x to the -1st, and then I'm going to evaluate that from 1 to t. So this is going to be the limit as t approaches infinity of -1 over t plus 1, right, minus -1. And then as t approaches infinity, well, -1 over t is going to approach 0. And so this equals 1. Well, what does this tell me? Well, remember from previous chapters, this means our improper integral converges, and by the integral test, we know that our infinite series, so the sum, n equals 1 to infinity of 1 over n squared, also converges by the integral test. All right, now note in general, whatever value you get for the improper integral is not equal to the infinite sum, okay? So for example here, when we evaluated the improper integral for 1 over x squared dx, the value of that came out to be 1, but that's actually not what the sum of 1 over n squared is from 1 to infinity. In fact, the sum from n equals 1 to infinity of 1 over n squared is equal to pi squared over 6. And if you ever take complex analysis, you'll see how you can find that sum. So notice it's not equal to 1. All the integral test tells us is whether it converges or diverges, but not necessarily what it will sum to. Okay, so now let's recap a little bit. Noticing here, the harmonic series diverged, but 1 over x squared or 1 over n squared converged. And that's because we can call them p series, much like we did when we were looking at improper integrals. So if you have the sum n equals 1 to infinity of 1 over n to the p, right? So if this exponent here, p, is between 0 and 1 inclusive, then the series diverges. So that includes the harmonic series when p equals 1. If p is greater than 1, then the series converges. That was like 1 over n squared that we just looked at here. What that means is when p is greater than 1, that's causing the denominator to grow faster, so the series is shrinking fast enough in order to converge as an infinite sum. And if p equals 1, it's the harmonic series. So from here on out, most of the time, as long as you just identify that a sum is a p series, you don't have to go through any testing in order to justify whether it converges or diverges. And then if you'll recall before, don't get this confused with geometric series where you have r raised to the n. And if absolute value of r is less than 1, then the series converges. And if the absolute value of r is greater than or equal to 1, then the series diverges. And remember, geometric series, if they converge, are very, very special because we are able to, in fact, compute their sum, their infinite sum. All right. Remember, s equals a1 over 1 minus r, only if it converges. All right, let's look at one more example of a p series. Here the directions say use the integral test to determine whether the series is convergent or divergent. Okay, can you already tell what's going to happen? I mean, this is a p series, and p is equal to 5, right? So this is a p series. P equals 5, which is greater than 1, which means the series converges. However, we're going to be obedient math students and use the integral test as the directions tell us. But it's nice to know what we should expect the outcome to be. So we're going to let f of x equal 1 over x to the 5th on the interval from 1 to infinity. And let's check our 3 conditions. So first, is it continuous on 1 to infinity? Well, yes, the domain is all real values of x such that x doesn't equal 0. So we're good on the interval from 1 to infinity. Is it positive on the interval from 1 to infinity? Yes, it is. I'm only substituting in positive values for x. And then is the function decreasing? Well, let's check its derivative. So f prime of x, remember f of x is x to the negative 5th, so f prime is going to be negative 5 over x to the 6th, and this is definitely less than 0. Denominator is always positive, numerator is always negative. So that means it's okay to use the integral test. And let's go ahead and set up our improper integral. So we have the integral from 1 to infinity of 1 over x to the 5th dx. I'm going to rewrite this as the limit as t approaches infinity of the integral from 1 to t x to the negative 5th dx. And then let's go ahead and anti-differentiate. So this is going to be the limit as t approaches infinity. I'm going to have x to the negative 4th, so I'm going to have a negative 1/4 x to the negative 4th evaluated from 1 to t. And this equals the limit as t approaches infinity. I'll leave the negative 1/4 factored out. And then I'm going to substitute in my limits of integration. So x to the negative 4th, substituting t for x, I'm going to have 1 over t to the 4th minus 1. And then now I can take this limit. So as t approaches infinity, 1 over t to the 4th is going to go to 0. All I'm left with now is negative 1/4 times negative 1, and this is going to leave me with a positive 1/4. So since this is a finite number, right, that means the improper integral converges. So the sum n equals 1 to infinity of 1 over n to the 5th also converges by the integral test. Make sure anytime you're testing for convergence or divergence of a series, you rewrite the original series in your statement. You clearly write out if it converges or diverges, and then you also include the test. Okay, this is something you need to get into the habit of doing throughout the chapter. Okay, now a few other examples. Notice here, now the directions just say to determine whether the series is convergent or divergent. So they're not instructing us what test or method we need to use. It's up to us. So notice here, I have the sum n equals 1 to infinity of n to the negative 1.4 plus 3n to the negative 1.2. Now what I'm going to do is separately consider each of these terms as individual infinite series and determine whether or not they converge or diverge before I can make a statement about the original. Okay, so first I'm going to consider the sum n equals 1 to infinity of n to the negative 1.4. And notice that's a p-series. I can rewrite this as the sum n equals 1 to infinity of 1 over n to the 1.4. So here's how you would use the fact that it's a p-series. You're going to first state that. Hey, this is a p-series. What is p? Well, p is 1.4. And guess what? That's bigger than 1. And what does that tell me? This means that the series converges. Okay? So make sure if you're not going to go through the whole integral test, which you really shouldn't, okay, then you clearly state this is a p-series, identify what p is, compare it to 1, and then state your conclusion. Okay, now I'm going to consider the next part. The sum n equals 1 to infinity of 3 times n to the negative 1.2. Well, I can take the 3 outside, so 3 times the sum n equals 1 to infinity of 1 over n to the 1.2. Notice this is also a p-series. What is p? P is 1.2, and that is greater than 1. So this series also converges. And if you have an infinite series that converges and you multiply by a constant, it's still going to converge. If you have a series and it diverges and you multiply by a constant, it's still going to diverge. So you can always pull out a constant and it will not affect the convergence or divergence of a series. Okay, so what can I say now since I know this part of our sum converges as well as this part? Well, now I can put them together, right? We have one of our infinite series properties, a theorem from earlier that said this means that the sum n equals 1 to infinity of n to the negative 1.4. Rewrite the original exactly how you saw it. Okay, don't change a thing. Plus 3n to the negative 1.2 also converges. All right, nice. Now don't be lazy. Don't just say, oh, converges, or draw an arrow. You must rewrite the original exactly as you saw it. Beautiful. Okay, let's look at this next series here. Notice they didn't write it for me in summation notation. They've just listed out the first few terms. So let's investigate what's going on. So we have 1/5 plus 1/8 plus 1/11. I notice the denominators each time are going up by 3. Okay, so that means this is not geometric, right? I'm not multiplying by a common ratio. And I don't see any signs alternating, right, with positives and negatives. So this is not a telescoping sum like we saw in the last section. And it's not a p-series. P-series is if you see n squared, n cubed, some power of n in the denominator. Can you write this out in summation notation? Maybe that'll help us get a feel for what's going on. So the denominator is always increasing by 3. You could just treat the denominator as an arithmetic sequence and then just put 1 over whatever expression you get. So notice I can write this as the sum n equals 1 to infinity. Since the denominator is going up by 3 every single time, you're going to have 3n. And then if you want the very first term to have a 5 in the denominator, then 3 times n, 3 times 1 would just give me 3. So I better add 2 and then put 1 over that. And that checks out, right? You can confirm. If I substitute n equals 2, that would give me the second term, etc. Ooh, that's not what I wanted. Okay. So all of the methods that we're thinking, geometric telescoping p-series, don't apply. Well, let's try the test for divergence. I mentioned in the previous video, you always want to check this first, at least mentally, okay, even if you don't write it out. So let's try the test for divergence or divergence test, meaning I'm going to take the limit as n approaches infinity of a sub n, of just the terms. 1 over 3n plus 2. What is that limit? It's 0. So what does that tell me? Nothing. This is inconclusive. Remember, the test for divergence only gives you information if the terms do not go to 0. Then you can say, oh, for sure my infinite series diverges. If the terms aren't going to 0, there is no way I could add them all up and have the sum converge, right? The terms at least have to go to 0. But if they go to 0, that doesn't give us any info. That's a necessary but not sufficient condition for convergence. All right, I'm all out of options, so let's try the integral test. Why not? That's the only thing we have left at this point. So let's try the integral test. All right, I have to check the conditions. So we're going to let f of x equal 1 over 3x plus 2. And I want to confirm, okay, is it continuous on the interval from 1 to infinity? Well, what's the domain for this function here? I could see it's going to be undefined at -2/3. So the domain is all x's such that x doesn't equal -2/3. But we're fine on 1 to infinity, right? That's not going to be a problem for us. So we're good. Is it positive on that interval? Well, yes, if I'm only substituting in 1 to infinity for x, we're good to go. And then is it decreasing? So again, I want to compute f prime of x in order to check. Now f of x is 3x plus 2 to the -1st power, right? So the derivative is going to be negative, then I'm going to have 3x plus 2 squared, and then by the chain rule, I need a 3 in the numerator. Well, the denominator is squared, so that's always positive, and then the numerator is going to be negative, so this is for sure less than 0. So yes, my function's decreasing, so that means we can use the integral test. Fabulous. Okay, so let's write out our improper integral. We have the integral from 1 to infinity of 1 over 3x plus 2 dx. And this equals the limit as t approaches infinity of the integral from 1 to t of 1 over 3x plus 2 dx. Okay? Now come on, at this point you don't need to do a full u sum. If I were to let this denominator equal u, then du would have a 3 dx attached to it. So I would have to divide, right, by 3 or multiply by a 1/3. So just add the 1/3 here and anti-differentiate appropriately. So we're going to have the limit as t approaches infinity of 1/3 times the natural log of the absolute value of 3x plus 2 evaluated from 1 to t. All right, and then now I'm going to substitute in my limits of integration. So this is the limit as t approaches infinity of 1/3. We have natural log of the absolute value of 3t plus 2 minus natural log. If I substitute in 1 for x, that's going to be 3 plus 2, so ln of 5. All right, now let's see. As t approaches infinity, 3t plus 2, that's going to go to infinity. So natural log of infinity, think of the graph. This is going to all approach infinity. ln of 5 is just a constant. So infinity minus a constant, this whole thing is just blowing up. So this limit is equal to infinity. So what does that tell me? Well, this means that the sum n equals 1 to infinity of 1 over 3n plus 2 also diverges by the integral test. Okay, and maybe you had an idea that that was going to happen because this reminds you of the harmonic series 1 over n. It just, now it's 3n plus 2. So it's pretty much shrinking or growing, however you want to think about it, at the same rate as the harmonic series, right? Now, if you had something with an n squared in the denominator, then that would grow like a p series with p equals 2. That would be shrinking faster. So you would expect something like that to converge. So just keep that in mind. All right, one more example here. Determine whether the series is convergent or divergent. And you know what? This is not written correctly. Hopefully your version looks a little different. This should be the sum n equals 1 to infinity. The e is raised to the 1 over n to the 7th. And then in the denominator, we have n to the 8th. Okay, I'm just going to go straight to the integral test. We're going to consider the function f of x, which is equal to e. Now, this is e to the 1 over x to the 7th over x to the 8th. Okay, good. Now, is it continuous on the interval from 1 to infinity? Well, what's the domain for this function? Well, the only value for x that I'm not allowed to use would be 0, right? All x's such that x doesn't equal 0. So we're good on 1 to infinity, no problems there. Is it positive? Well, I know e to the x is always positive, x to the 8th is always positive, so we're fine. What about if it's decreasing? Ooh, well, I need to look at its derivative now. Okay, let's rewrite it so we're ready to take the derivative. This is e raised to the x to the negative 7th over x to the 8th, right? So I'm going to have to use the quotient rule. So f prime of x is going to equal, I have the denominator, x to the 8th times the derivative of the numerator. So derivative of e to the x to the negative 7th is going to be e to the x to the negative 7th. And then by the chain rule, I have to multiply by the derivative of the exponent. So I'm actually going to have a negative 7x to the negative 8th, right? And then e to the 1 over x to the 7th. So that's low d high, if you think of it that way, minus the numerator, so that's e to the 1 over x to the 7th, times derivative of the denominator, which is 8x to the 7th, over denominator squared, x to the 16th. And remember, I just want to investigate whether the derivative is positive or negative. So let's see. Ooh, can I factor out a common factor? Yes. I can take out, watch this, I can factor out the e to the 1 over x to the 7th, right? Okay, so I take that out, e to the 1 over x to the 7th. What am I left with here? Well, I have this x to the 8th is going to cancel with x to the negative 8th. So all I have is negative 7 minus 8x to the 7th. Whew, that cleaned up nicely. Over x to the 16th. Okay, now let's look at this. E to the 1 over x to the 7th, that's always positive, right? Think of your graph of e to the x. X to the 16th, that's always positive also. Now what about negative 7 minus 8x to the 7th? Remember, we're only considering x's from 1 to infinity. X is always greater than or equal to 1. So if I'm only plugging in values for x that are greater than or equal to 1, negative 7 minus 8 times something greater than or equal to 1, this is always going to be negative. So for sure, I can say the derivative is negative on this interval, so it's decreasing. Great. All that means is I'm allowed to use the integral test now. So let's do it. So we have the integral from 1 to infinity of 1 over, or let me rewrite it as e to the x to the negative 7th over x to the 8th dx. Good. So this is an improper integral. I'm going to rewrite this now as the limit as t approaches infinity of the integral from 1 to t. And then the denominator, I'm going to write it as x to the negative 8th and then e to the x to the negative 7th dx. Ooh, no negative there. All right. And here, hopefully you can see that we're going to need to do a u substitution. We're going to let u equal x to the negative 7th, the exponent here. And then du would be negative 7 x to the negative 8th dx, which we have right here. Okay, so I can rewrite this now as the limit as t approaches infinity. Now it's up to you. If you're going to leave your limits in terms of x, 1 to t, then you need to indicate that you're not changing them when you do the u sub. So this is x equals 1 to x equals t. Otherwise, change them. Okay. And then we're going to have a negative 1/7 e to the u du. If I anti-differentiate, that's just going to give me e to the u. So this is the limit as t approaches infinity, negative 1/7 e to the x to the negative 7th from 1 to t. All right, now substituting in our limits of integration, we have the limit as t approaches infinity of negative 1/7. Leave that outside so you don't get all confused. So this is going to be e to the t to the negative 7th minus e to the 1st. So t to the negative 7th, as t approaches infinity, that's 1 over t to the 7th. So this exponent is going to be approaching 0. And e to the 0 is going to be 1. So this limit here is negative 1/7 times 1 minus e, which I can rewrite as 1/7 times e minus 1. I don't really care what it comes out to. All I care is that it's finite and the improper integral converges. So what this means is my original series, n equals 1 to infinity, of e to the 1 over n to the 7th over n to the 8th also converges by the integral test. Okay, nice job. Now to summarize what we've covered thus far in the chapter, take a look over here on the left. And we've gone over geometric series in our previous lessons. Remember, if the common ratio is less than 1, the series converges. If the common ratio is greater than or equal to 1, it diverges. P series, we've looked at P series today. If P is greater than 1, the series converges. If P is between 0 and 1 inclusive, it diverges. Harmonic series is a P series where P equals 1. The test for divergence, you always need to check if the terms do not go to 0 or if their limit doesn't exist, the series diverges. Okay, an example would be maybe you have the sum n equals 1 to infinity, something like 2n plus 1 over n minus 3, right? This diverges as an infinite series because the limit as n approaches infinity of a sub n. A sub n is just the terms, right? What's the limit of those terms? It equals 2, which is not 0. Now, don't get this confused with just the very first section in this chapter, sequences. So a sub n equals 2n plus 1 over n minus 3. If I just said, hey, does this sequence converge or diverge? It converges. It has a finite limit. So it converges as a sequence, but not as an infinite series, right? In order for the sum to converge, the terms have to be at least going to 0, and they have to go to 0 fast enough so that if you add them up, the infinite series approaches a finite number. All right, you can also use the squeeze theorem, and we considered an example with sine and cosine where that worked out nicely. And then now our new test to add to the list for convergence or divergence is the integral test. And make sure you memorize the conditions that go with applying the integral test. 3 of them. F has to be positive, continuous, and decreasing. All right, that concludes the lesson, and stay tuned for more tests for convergence or divergence.